Alright, good morning and selamat pagi, Assalamualaikum. Okay, today we'll continue on the next chapter, which is one-dimensional conduction. So this is basically what we will cover lah. So have a look on it. So perhaps we understand multi-dimensional, what is multi-dimensional, and we look on thermal resistance and the limitations, and then develop understanding of thermal contact resistance, identify applications which insulation may actually increase the transfer, and then analyze fin surface, and also evaluate heat conduction in solid temperature dependent thermal conductivity. Right, introduction. Heat and temperature are closely related, but they are different in nature. So temperature has only magnitude, and it is scalar quantity, means doesn't have any vectors, any directions. Temperature doesn't have any direction, but heat transfer have directions. That's why we call it vector quantity. So we work with coordinate system and indicate direction with plus and minus sign. So this is how we indicate plus minus sign to show whether it is either in correct way or reverse. So perhaps here, as you can see, this is a hot potato bag. So heat is being transferred out. We have this one magnitude of temperature at point A, no direction. This is 50 degree and 50 degrees Celsius. So this is scalar quantity, this temperature. But we have another one. This is 80 watt per meter square. This is heat transfer. It has magnitude, and also it has vectors, direction and magnitude. And then magnitude and direction of heat flux at the same point. Okay, here it shows that it have a heat flux. Heat flux means, why heat flux? Heat flux actually is Q equal to Q over E. This is unit. The unit is watt per meter square. This is heat flux. Q is joule per second, or is equal to watt, joule per second. This is Q, Q dot joule per second. If Q only, this is joule, J. Okay. Then we have here we have indicating direction of heat transfer, positive and negative direction. Here we have hot medium, cold medium. So Q is positive, means Q is being transferred from hot to cold medium. This is the correct way of heat transfer, from hot to cold, which is Q dot equal to 500 watts. L is the thickness, or X. And then we have here minus Q equal to minus 500 watts. This indicates that the heat is being transferred reversely, from this is seems from hot to cold, but the X is in reverse direction. So then another case that it being transferred from reversely, from cold to hot. It's minus, means that it's supposed to be the heat is transferred on the other directions. Okay, the driving force from any form of heat transfer is temperature difference. So basically, when we have a temperature difference, when you have two types of body, for example, this is 50 degrees Celsius, this is 40. So because of this temperature difference, heat will be transferred from hot to cold. If this one is 40 degrees Celsius, it's also 40 degrees Celsius, this point and this point, the temperature difference is equal to 0. I mean, no heat being transferred because it's already in equilibrium. Okay. The larger the temperature difference, the larger the rate of heat transfer. So if you need something to be transferred in large amount, Q1 is big, you increase the temperature difference. This also could be seen by if we have this so the Q equal to, the formula is equal to Q equal to Ka delta T over L. So here, as you could see, this is Q is proportional to K, Q is proportional to A area, Q is proportional to temperature difference, Q is inversely proportional to 1 over L. So means that when Q is high, K is also high. Q is high, this is also high. When this is low, this is also low. Okay? Because it's directly proportional. High means this one also high. If this is high, this will become low. If this is high, this will become low. Okay? Inversely proportional. So here we have, for example, we have rectangular coordinate, we have here cylindrical coordinate, we have here spherical coordinate. As you can see, this is example x, y, and z, x, y, and so and z. So here we have a point Q, P, P, and P. So we have x, y, and z are this is psi, z. We have r, psi, and theta. So this is the coordinate of the point. Okay. Steady versus transient heat transfer. Steady implies no change with time at any point or medium. Transient implies variation of times or times dependence. So here, as you can see, this is example of steady states. Means from 2 p.m. up to 5 p.m. the temperature difference is still the same, for 15 degrees Celsius, 7 degrees Celsius, 15 and 17. So Q1 is equal to Q2. I mean, this is in steady heat transfer. But if 2 p.m. the 15 degrees Celsius, then it changed to 12 degrees Celsius, 7 changed to 5 degrees Celsius because of because of something else happens. So this is, we call it transient heat transfer, because it involves the times dependent. So because of the time, maybe this 2 p.m. the sun is very hot. At 5 p.m. the sun is already going over the mountain, perhaps. I don't know. Okay, so the light intensity is reduced. Okay, in this there is a system, we call it lump system, where it's vary with time but not with positions. Okay? So this is for example, we have a lump systems. This is just a knowledge. You could Google it. So this is a lump. So perhaps from time to time the temperature is changing, but from this position and this position or this position, the R is different, right? The R is different, or the length is different, but the temperature for T for every point is the same. But when the time is 2 p.m. for example, and change to 2.5 15 p.m. so every T will be changed, right? Multi-dimensional. So here there are actually heats is being transferred not in one direction, so it being transferred in every direction. Perhaps this is, we call it three-dimensional, up to three dimension. So as you can see here, for example, here heat being transferred from left to right. and then we have here front to back, and also from top to bottom, or top to bottom, or bottom to up. So this is actually heat radiation transfer. This is we call it two-dimensional because it only have left, right, front to back. But normally when we have a heat transfer, we only assume that heat is being transferred in one direction, because the other, or the rest, we neglect because of the we don't want to count it, or the Q is very small compared to the other one. So that's why we neglect. So here is only 2. If it has another one, so perhaps it can go from top to bottom, or bottom to up. So this is 3-dimensional. If it has another one, so this is also 2, but heat transfer towards the in the wall, we neglect it. We just assume that it is being transferred from inside of the building to outside. Okay, here why heat is being transferred from inside to outside, because this is chimney. Chimney means this is house for 4-season country. They have burn something inside, and outside is very cold, so heat is being transferred from hot to cold. Okay, here we have the Fourier's law of heat conduction. The Fourier's, that the person that create this kind of equation. Q conduction is equal to Ka delta T over L. Delta T over L dt over dl dx. So minus means that supposed to be in another way. Heat is conducted in direction of decreasing temperature, thus temperature gradient is negative when the heat is conducted in positive direction. This is why negative. Okay, basically, if you could see here, rate transfer into the wall minus heat transfer out from the wall equal to rate of change of energy of the wall. So Q in minus Q out is equal to d E wall over dt. The E wall means energy. Different the rate transfer of energy over dt. So the best one, you just remember this one, produce law of heat conduction. So here Q T1 minus T2 is dt. So T1 20 minus 3. So X we have here, doesn't put any X. Here, conduction. Here example of same material. As you could see, this is T is actually drop when it goes from one material to another one. But the K is almost the same. That's why this is straight line. Or the K doesn't reflect so much. Then we have a decreasing of Q conduction. Okay, here is something else. If the material number 1 and material number 2, the value of K is very different. Not equal, actually, not equal, and also very huge difference. Then the slope of Q, or the slope of T1 minus T2 is is larger compared to the other one. So because of difference of k, too much difference. If not, it will look like this. Okay. Okay, this exercise for you. No need to submit. So here we have a metal over here, and the length is 8 cm, 90, 10, and then we have thermal conductivity K equal to 200 watt meter Kelvin. Just use this number, doesn't need to change it. Doesn't need to change it. So 90 minus 10, you don't need to change the value. You can try to change the value if you like, but you will get the same answer. You got the same answers. So for easiness, don't change any value except this one. You need to change to meter. Okay, ATM need to change to meter. So just use the formula given. Q equal to Ka dt over dx, and you got the answer. Okay, please submit it. Temperature gradients means it's only need dt over dx. And the one needs Q, quantity heat flow cube in 3 minutes, means you need Q dot. Okay, this is Q dot, this one is dt over dx. Next one is this is plain wall. Different T is 120 minus 50. X is already been given. K is 1.2 watts meters degree Celsius. So calculate the Q. Okay, and then variation of temperature with the wall and the temperature value. So then change the wall to 0.1. Okay, if you change value 0.1, then what happened to the dt? What happened to the dt? Variation of temperature. So here you need to find dt, and assuming that Q is the same. Number 2. Number B is Q is equal to the one that you get from here, Q dot. Then you change X equal to 0.1, then find dt. Okay. Q Ka dt over dx. Find dt. Okay. The rest you put the other one because Q is the same. Okay, please submit it. Thank you. Assalamualaikum.